Dear students, welcome to the second lecture on units and measurement of class 11 physics. In section 2.1, I will introduce the topic units and measurements followed by the international system of units. The points discussed are important. Please open your notebook and note down all the points. Measurement of any physical quantity involves comparison with a certain basic arbitrarily chosen internationally accepted reference standard called unit. The result of a measurement of a physical quantity is expressed by a number or numerical measure accompanied by a unit. Although the number of physical quantities appear to be very large, we need only a limited number of units for expressing all physical quantities since they are interrelated with one another. Physics is a quantitative science based on measurement of physical quantities. 7 physical quantities, namely length, mass, time, electric current, temperature, amount of substance, and luminous intensity have been chosen as fundamental or base units. All these 7 base units are listed in table number 2.1. Each base unit is defined in terms of certain basic arbitrarily chosen but properly standardized reference standard called unit, such as meter, kilogram, second, ampere, Kelvin, mole, and candela. The units for fundamental or base quantities are called fundamental or base units. Other physical quantities can be expressed as combination of base units and are called derived units. I will repeat once again. Other physical quantities can be expressed as combination of base units and are called derived units. A complete set of units, both fundamental and derived, is called a system of units. International system of units. The International System of Units (SI) is based on 7 base units and is at present internationally accepted unit system and is very widely used. In earlier times, scientists of different countries were using different system of units for measurement. 3 such systems were the CGS system, the FPS or British system, and the MKS system were in use extensively till recently. The base units of length, mass, and time in these systems were: in CGS system, it was CGS means centimeter, gram, and second respectively. In FPS, that is foot, poundal, and second system, they were foot, pound, and second respectively. In MKS system, they were meter, kilogram, and second respectively. The SI units are used in all physical measurements for both base and derived units. Certain derived units are expressed by means of SI units with special names such as joule, Newton, watt, etc. So, joules, Newton, watt, etc. are derived units, whereas the base units are the 7 which were listed earlier. The SI units have well-defined internationally accepted unit symbols such as small m for meter, kg, small k and small g for kilogram, and small letter s for second, and capital A for ampere, capital N for Newton. Please note small m for meter, small kg for kilogram, small s for second, capital A for ampere, and capital N for Newton, etc. Physical measurements are usually expressed for small and large quantities in scientific notation with powers of 10. So we use multiplier as 10, and whenever it is smaller quantities are there, the power or exponent is minus. It is indicated with minus. And when large quantities are there, the power is plus. And a list is also list of these powers are given in appendix A in subsequent slide. Scientific notation and prefixes are used to simplify measurement notation and numerical computation, giving indication to precision of the numbers. So these notations are also listed in the appendices and subsequent tables. Some of the old system of units were CGS, centimeter, gram and second, FPS, foot pound second, MKS, meter kilogram second, as explained earlier. In the table 2.1, SI base quantities and units have been given. Here in this slide, we will define the base quantities and units. Length, that is meter with symbol small m, is defined by taking the physical value of speed of light as to be 299792458 meters per second. The second base quantity, mass in kilogram, is defined by taking fixed numerical value of Planck's constant h to be 6.62607015 into 10 to the power of minus 34. So Planck's constant does not have any dimensions. It is a constant, and when we express this in joules, it is kg meter square per second. So kg is defined here. So time in seconds, S, is defined by taking fixed numerical value of cesium frequency. Cesium frequency, that is delta V subscript Cs, the unperturbed ground state of hyperfine transition frequency of cesium-133 atom 91926317770 when expressed in unit hertz, that is s to the power of minus 1, that is 1 over s. The electric current ampere capital A is defined by taking fixed numerical value of charge 1.6021766634 into 10 to the power of minus 19 when expressed in the unit C, which is equal to ampere seconds. Temperature, when Kelvin, is defined by taking fixed numerical value of Boltzmann constant K to be 1.380649 into 10 to the power of minus 23 when expressed in unit joule per degree Kelvin, which is equal to kg meter square per second square per degree Kelvin. Amount of substance mole, that is mole. 1 mole contains exactly 6.02214076 into 10 to the power of 23 elementary entities. This number is fixed numerical value of Avogadro constant Na when expressed in the unit mole per mole and is called the Avogadro number. The amount of substance symbol M of a system is a measure of number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, or any other particle or specified group of particles. Finally, luminous intensity expressed as candela is defined by taking fixed numerical value of the luminous efficacy of monochromatic radiation of a frequency 540 into 10 to the power of 12 Hz. KCD to be 683 when expressed in the unit lumens per watt, which is equal to candela SR per watt or CDSR per kg per meter square second cube S cube. Here the second is defined in terms of cesium frequency delta VCS. Meter is defined in terms of velocity of light, and kilogram is defined in terms of Planck's constant, velocity of light, and frequency of cesium. It may please be noted the values mentioned here need not be remembered or asked in the examination. They are given here only to indicate the extent of accuracy to which they are measured. With progress in technology, the measuring techniques get improved, leading to measurements with greater precision. The definitions of base units are revised to keep up with this progress. Table 2.2 shows some units retained for general use, though they are outside the SI unit. So, minute we had expressed previously in seconds. Time is expressed in second, but sometimes we use minute. Minute is 60 seconds. Hour, sometimes we mention hour. Hour is 60 minutes is equal to 3600 seconds. Day is 24 hours, that is 86,400 seconds. Year is expressed and its value is 365.25 days, that is equal to 3.156 into 10 to the power of 7 seconds. Degree is 1 degree is equal to pi by 180 radians. 1 liter is decimeter cube, that is equal to 10 to the power of minus 3 meter cube. Sometimes we use tons. Tons is small t and it is 1000 kgs, that is 10 to the power of 3 kgs. Carat is C, small letter C, and 1 carat is equal to 200 milligrams. Bar is the unit for pressure. Bar 0.1 MPa is equal to 10 to the power of 5 Pa. Curie Ci is one of the 3 units used to measure the intensity of radioactivity in a sample of material. This value refers to the amount of ionizing radiation released when an element such as uranium spontaneously emits energy as a result of radioactive decay or disintegration of an unstable atom. It is equivalent to number of atoms decaying per second. Its value is 3.7 into 10 to the power of 10 per second. Roentgen, capital R, 2.58 into 10 to the power of minus 1 C per kg. Quintal. Quintal is 100 kgs. 1 quintal is equal to 100 kg. Barn, small b, 100 f, fm, f into m square. That is 10 to the power of minus 28 meters square. AREA is equal to 1 DAM square is equal to 10 square meter square. Hectare, 1 hectare is equal to 1 hectare meter square is equal to 10 to the power of 4 meter square. Standard atmospheric pressure is ATM is equal to 101325 PA, that is equal to 1.1013 into 10 to the power of PA. These items we will be using as and when required, but these are not listed as SI units. Appendix A shows the SI prefixes and symbols for multiples and submultiples. Please see here the factors are ranging from 10 to the power of 18 plus 18, that is exa, and symbol is E. So different multiples, prefixes and symbols for multiples and submultiples are given. Here some important are tera T, that is 10 to the power of 12, and giga is 10 to the power of 9, and mega is 10 to the power of 6, and kilo is 10 to the power of 3. Tera, giga and mega are extensively used in data communication where we use terabyte, gigabyte and megabyte. Kg is used in weights and measure. Similarly, in the submultiple range, we use pico, that is 10 to the power of minus 12 is pico, small p, and 10 to the power of minus 9 is nano, small n, and 10 to the power of minus 6 is micro. These three are extensively used to indicate the capacity of capacitors like picofarads, nanofarads, and microfarads. These things we will study in detail in class 12. Similarly, milli is used 10 to the power of minus 3 milli, small m, and centi. Centi is 10 to the power of minus 2. These two are used in measurement scales, measurement of length. This appendix B shows the Greek alphabets and symbols used in physics. You simply go through it and you can note down in your records. So these will be used as and when you come across these subjects. Like Greek words alpha is used for angles and coefficient. Nu is used for frequency. Beta is also used for angles and coefficients, so on and so forth. So you note down just for your reference purposes. This is given as appendix B. Supplementary units. Apart from basic units, we have certain supplementary units. Like phase angle d theta is equal to length of an arc ds divided by radius. There are two supplementary units that are defined for plane angle and solid angle. Please see the figure. Figure A is for plane angle. Here plane angle means it is two-dimensional figure. Here O is the origin point and ds is the arc of a circle and r is the radius. And d theta is the angle subtended by the arc of circle ds. Hence d theta, that is plane angle, is equal to length of arc ds divided by r. So this is a plane angle. And another supplementary, this plane angle is expressed as rad or radians. It is defined as the plane angle subtended at the center of the circle by an arc of a circle equal to its radius. As explained, d theta is equal to ds by r radians. Solid angle. This figure B shows the solid angle. Here we are using the 3 dimensions. So we are using the spherical surface. Solid angle d omega is equal to intercepted area of spherical surface dA. You see spherical surface is dA. It is intercepting the angle subtended at the O divided by the radius r. R is the radius. This is referred in figure 2.1b. Steradians. Solid angle is mentioned as steradians, that is SR. It is defined as the solid angle subtended at the center of a sphere by an area of sphere equal to the square of its radius. See, this is the angle, solid angle d omega. D omega is the angle subtended by the surface area dA at the center O. International system of units. Advantages of SI system over other system. SI is coherent. Coherent means logically connected, consistent, orderly, or integrated. So SI is a coherent system. SI is a rational system. Rational means based on clear thought and reason. So SI is based on clear thought and reason. SI is an absolute system. Absolute means total and complete, perfect, free from imperfections. SI is a metric system. As you all know, it is a metric system. The symbol for units, it is a note here. Please note, the symbol for unit is written with a small letter. Example, meter, kg, s, mol, and cd. The symbol for units named after a person, that is a scientist or a physicist, is written in capital letter. That capital N is written for Newton and capital A for Ampere. Full stops or other punctuation marks are not written. Please note, full stops or punctuations are not written after symbol unit. Example, for kg, we don't write k dot g dot. We write simply kg, meters per second. With this, we come to the conclusion of introduction and SI units. In the next lecture, we will study measurement of length, measurement of mass, and measurement of time. Till then, goodbye.